speaker is Dr. Andy Davids, who is a director of the global consulting engineering practice Hyder Consulting and serves on the Hyder Global Professional Board. He is the chief engineer of the Hyder Design High-Rise Design Studio, which is now based in Dubai and is responsible for many of the high-rise projects undertaken by Hyder around the world. Andy's studio currently has 7 towers between 60 levels and 160 levels, under various stages of design and construction. He is an adjunct chair in architecture at the University of Sydney and was recently cited as amongst the 100 most influential Australian engineers. Andy.
Thank you, Mr. Chairman. Ladies and gentlemen, welcome to Dubai. And thank you, Sean, for that amazing presentation. I think what Sean showed us just then is the entire conference in one building. Truly remarkable, a fantastic presentation. Very difficult act to follow. My offering this morning to you is called A Postcard from the Gulf, and I've titled it, The Social, Economic and Natural Forces which Shape Our Tall Buildings Locally. Now what I hope to do is to take you through a short journey to take you through some of these influences that shape the buildings that we're producing here and how they may be different to the parts of the world that you come from, and follow up with 3 or 4 examples of buildings under construction, and you can see those forces at work. The first, I think, is context. Context is very, very important. I think as architects and engineers living and working here in the Gulf as we do, we're creators. We're out here because we enjoy creating, and we need to ask ourselves, before we turn our hand to that, what's the context of our creation? Why are we here doing all these fantastic things? And the answer is quite simple. I think a casual observer to Dubai would think that it was just a shallow display of wealth fueled by oil money. And I can tell you that nothing is further from the truth. Living and working here, as I do, and many engineers and architects do, what we can tell you is that it's an act of nation building. There's a lot of nation building going on in the Gulf at the moment, and we need to remember that, because most of us come from places that have long-established traditions and senses of place and senses of being and senses of community, which, quite frankly, didn't exist here until quite recently. And when you're trying to build a community, these icons, whether they be buildings or Emirates Airlines, these things that people can hold up as their own are very, very important when you're trying to build a nation. So that's really the context of what we're doing here. Let's move on to some of the natural forces at work. We ask the question, many people ask us, how can we build all these tall buildings here in the Gulf on sand? Is it a suitable material? So there's a typical geological profile cut through here. This is the profile cut through the Emirates Towers, actually, just down the road. What you can see is that there's perhaps 5 or 10 metres of fairly soft sand, and it's not good stuff to build on. Typically we have then layers of conglomerate and marine sediment, which is actually very strong. It's very strong material, and then into deeper layers of the same sort of stuff. So I think the sound bite from this slide really is that the material here is strong, it's good, it's certainly capable of holding very, very heavy buildings, with one perhaps slight exception, and that's that when we test this material, we see that because it's marine sediment, under cyclic action it tends to degrade. The strength tends to degrade a bit. That's important for piles, deep piles that are in the corners of buildings. Because as a building sways around in the wind like this from side to side, the piles around the perimeter tend to have a cyclic loading on them, tension and compression and so on. And under those conditions, the pile in the marine sediment can lose strength, perhaps 25% of its capacity. We need to keep that in mind. Engineers love breaking things. Eventually we turn the computers off and go build and break it. And this is a slide here showing in the right-hand corner a pile for the Dubai project, actually, which Bill Baker will tell us all about in much more detail tomorrow. But this particular pile was about 50 metres long, 1.5 metres diameter. That's a typical sort of pile we use here for a high-rise building. They have a capacity of perhaps 3,000 to 5,000 tonnes. each, so they're very high capacity. The slide in the centre there is an illustration of a typical foundation system that we use in the Gulf for these high-rise buildings. In that particular case, it's the Burge Foundation, which has about 200 of these piles buried into the marine sediment, overlain by about a 5-metre thickness of concrete, a raft, a big solid raft of concrete. Piles take about 85% of the load, and the raft itself about 15% in bearing. That's a typical sort of foundation that's used in the Gulf here. So they're very strong, very stable. To date, we've measured about less than 50 millimetres settlement, even on the foundation of Burge. So they're quite stiff as well. Okay, we asked, what about the earthquake environment in the Gulf? Is it particularly seismic? I don't know if you remember back to your geography lessons in school and how the Earth's surface is made up of plates, very much like the plates on a baby's head when it's born. They're all moving around a little bit. We're on the Arabian plate here, and to the north of us is the Eurasian plate. Our Arabian plate is moving north at about 20 to 25 millimetres per year, something like that. So it's quite a high-speed plate. It's colliding with the rest of Asia and being pushed down. And those little red dots there on the map represent seismic events through the Zagros Mountains. So it's a very seismic area up to the north, but fortunately on the southern shores of the Gulf there, we're 400 or 500 kilometres away from that. When we look at the acceleration spectra for the ground conditions here, it's in fact, interestingly, less seismic than the southeast of England, which had an earthquake the other day. So I think the soundbite from this slide is that it's not a particularly seismic zone on the southern shores of the Gulf, but on the north it certainly is. What about wind? What's the wind environment in the Gulf? Is it different to where you all come from? Well, I think to answer that question, we need to just drill into wind a little bit. Wind is made up of 3 or 4 major sorts of events. The first kind of event is what we call a large-scale synoptic event, and this radar image here shows a very large pressure system, typical of the pressure systems you get all around the world. This particular one coming into the east coast of the United States. That's the kind of thing you see on a weather map. They're characterised as moving fairly slowly. They're a large diameter, and they're very predictable in particular seasons and cycles. When we launch balloons through them, we get velocity profiles as shown on the right-hand side, and it's all very predictable. So yes, we get those sorts of pressure systems here, nothing to be alarmed about. This one is special to us. This is called a shamal. Shamal is an Arabic word meaning north, and more exactly it should be called northwest actually, because as Sean pointed out, there are seasonal winds here, particularly in late summer and late spring, which are very, very strong winds. They come from the northwest down the Gulf. On the photograph on the left-hand side, the satellite image shows the Gulf on a good day. And on the right-hand side, when a shamal is blowing down from the northwest, and you can see it's picking up half of Iraq and most of Kuwait, dropping it out into the Gulf there. A little bit more detail on that. Actually, the photograph on the left-hand side here shows a very strong shamal-like condition picking up a lot of Egypt and taking it out into the Mediterranean there. The velocity profiles shown in the upper right-hand side are quite different to the large-scale synoptic events. The shamal has a bullnose kind of velocity profile where the velocity actually decreases with height. So you get very, very strong winds down near the ground, perhaps 200-300 metres up. But up at 400, 500, 600 metres where we're building buildings now, the velocities actually drop off. So these winds are felt from the northwest at certain times of the year, but they have a particular velocity profile. The other sort of wind event we get here, and you would get from where you're coming in anywhere else in the world, is a thunderstorm downburst. The way that works is that when a cloud collapses, the dense air drops down and it strikes the ground and runs out, very much like pouring water out of a bottle onto the ground. It hits the ground and runs out. You get a high velocity jet of air that runs along the ground. These are characterised as coming from any direction. They occur in very, very specific seasons, and the velocity profiles are as shown on the right-hand side. Again, maximum velocities down near the ground level. So you get those elsewhere. This is one that you may not get. This is an event that we have occasionally. Indian Ocean cyclones cook up and zip across the Indian Ocean and make landfall in Oman or Iran. This is a photograph of Cyclone Gonu, which visited us around about this time last year. And at its track is shown on the right-hand side, different colours representing the different strengths of the cyclone. At peak, when the cyclone track is shown purple, and the photograph is looking straight down the eye, it had a strength of 5.5, which is the same strength as Cyclone Katrina, which devastated the United States. So these sorts of events are wandering around our area. We have to be careful of those. So what happens when we put all of this stuff into the wind tunnel? There's some photographs here from Peter Irwin's wind tunnel at RWDI. On the left-hand side, you can see a model, a 90-storey building, a model of in the tunnel. The upper photo showing a velocity profile that we test for a normal sort of large-scale synoptic event. And on the bottom, where we've placed some interference in the tunnel there at the bottom and at the top, which tends to give us quite a different velocity profile, the Shamal profile, or thunderstorm one. And the graph on the right-hand side, showing the blue lines are the response of that building to the synoptic events, and little dots in the middle are showing the response to thunderstorm and Shamal events. So generally the synoptic events are governing, provided that you tease them out of the data set. Okay, what else? Construction technologies available in the Gulf. I think there's a bit of a misunderstanding that Dubai is a concrete town. I can assure you that every sort of construction system that's available anywhere in the world, whether it be steel, concrete, high-strength concrete, post-tensioning, precast, it's all being used here. It's all readily available, good quality. So we're using all the different sorts of construction systems available. What about costs? This is an interesting one. I'm sure you can't read this, but this is some cost indices for about 20 or 30 different countries in the world. The upper dark blue countries tend to be European sorts of countries. It's all been normalised with respect to the cost of building in southeast of London. And what you can see at the very top is that the UK costs are obviously the index of 100. The more expensive countries are some of the Scandinavian ones, Denmark and Sweden and so on, Germany perhaps. Down the bottom of this curve, some of the lighter blue dots that are sort of sitting off to the left are the cities of Dubai and Abu Dhabi. In general, construction costs here per square metre are something like a half to three-quarters what they would be in the southeast of the UK. So on a global basis, it's still a cheap place to build. The pie chart on the right-hand side shows where the money goes in a typical 50-storey building. Perhaps 30% on services, 25% on planning, 20% on structure. No surprises there. The next curve, however, is the one that really drives what's going on in the construction industry at the moment. This is a curve of the cost of construction versus time. Across the bottom is a 2-year cycle, in a couple of month periods, and going up as an index starting in January 06, the index started at 100. So within a 12-month period, the costs have gone up something like 20% to 30%, and then another 20 to 30% the year after. The red and blue lines are the cost of materials, and the green line the cost of labour. So this curve is what drives our life at the moment. What we learn from this curve is that the rate of inflation in the construction industry in the United Arab Emirates is something like 19%, something like that. So that speed is king. We have to abandon the ways that we've been designing and building these high-rise buildings and refocus on speed. And I think the examples coming up will show you that. So here's some postcards from the Gulf. We'll just take a quick tour through a couple of different cities. The first one, Dubai, the Emirates Towers here in Dubai. The project, I'm sure you've seen it out the window there. It's basically 2 buildings, one 355-metre office building and the other a 305-metre hotel. This is a shot of some images of the office building. The construction system is shown in the middle there. It's a cast in situ raft with piles and so on. Central core with some outrigger bracing, which stiffens up the building. The frame system there was of precast concrete, spanning onto simple steel perimeter beams and concrete-filled steel tubes. Cycle time on that building was about 3.5 days per floor. Very, very fast building. The other thing we did on that building was to slide up to about 75 metres and put trusses across and start building the typical floors quickly as first off, and then bring a second construction crew in underneath to complete that building. So we had 2 construction crews working one above the other to save about 4 or 5 months off the construction program. This is the hotel town. Same sort of idea here, but being a residential or hotel building, the core was very small, of course, so it wasn't able to take the wind loads on the building. So in that case, we slipped up to the perimeter of the building, put some trusses across and launched the jump forms for the entire building off the perimeter. And it's a bit like squeezing toothpaste out of a tooth, out of a tube. The entire building just jump formed. Very, very fast. Next example over in Doha, a 90-level building, the Dubai Tower Doha, under construction at the moment. Ground conditions there quite good, in fact a little better than in Dubai. We've got some limestone there to sit on. Very interesting shaped building. I think an observation I'd make here about the new generation of 100-storey buildings that we're doing now, they all tend to be mixed use. All the owners want a hotel and residential and service departments and office, all within the same complex, within the same tower in fact. And that puts some challenges on us. The core, of course, is a big challenge, but more importantly, the stacking of all these things. How should we stack them one on top of the other? And what we've discovered, I think, is that the thing that governs fit out, the thing that governs the time you can hand over the building is the fit out time for the hotel. So that we tend to use steel in the bottom of these buildings to get up to the level where the hotel is and flip it back to cast in situ, flat pack concrete, which is what we're doing in this building here. No tour through here could be complete without some photographs of the Burj Tower, and I'm certainly not going to talk about Burj at any length here. This Bill's going to give us a fantastic presentation tomorrow. But really the soundbite from these slides is to show you that that particular project is a dead simple structure, beautifully simple structure to build. All of the vertical elements on this building, bar none, were captured into the self-climbing jump form, and that design feature of the original design allowed us to build this building on a 3 to 4 day cycle per floor. This is absolutely critical when you're building 160 floors, because if you're drifting out to 5 or 6 days, that's an extra 2 days per floor times 160 days, which is perhaps another year on the construction. And with a 20% inflation rate, you're dead in the water. So one of the lessons from this building is keep it simple, capture everything into the jump forms if you can, and keep going. A very, very fast building. Interesting little feature on this building, as you know, the dynamic characteristics of buildings are something that we assume as designers and that are rarely measured. We've had the opportunity on the Burj to measure some of the key dynamic characteristics of the natural frequency and damping. We do that quite regularly by using the tower cranes on top, holding them out to the side and bouncing concrete weights up and down, and measuring the decay spectrum and doing a fast Fourier transform on that, as you can see on the curve at the bottom. Can pick out the natural frequencies of the building, and we're pleased to report the building is behaving exactly as predicted, as these very, very large elastic objects do. I think the last project here is in Abu Dhabi. It's the Shams Al Marine project. Here it is here, 2 towers. It's about 80 levels under construction at the moment. And again, it's a mixed-use project with an office development at the bottom, residential on the top. So again, we're using steel and precast in the lowest 40 floors or so, and flipping back to cast in situ concrete above that. So spending the money on the steel to get up to the area where you need to start fitting out, and then perhaps going for something slightly slower, because at that point you can deliver floors much quicker than you can fit them out. Interesting feature of that building was the shape. During wind tunnel testing, the shape we thought was very aerodynamic, except for one particular wind direction, which caused us a few little problems, as you can see by the curve of response versus wind direction. Quite savage vortex shedding off one particular direction with very, very low damping. And that was cured easily by putting in some simple water tanks in the roof to provide a tuned sloshing damper for that particular characteristic. So very large-scale dampers are being employed here in the Gulf. Okay. And we're nearly done, Mr. Chairman, thank you. Can't leave without mentioning some of the studio research currently underway here. we're looking at what the change in climate might be here in the Gulf. I think it's incumbent upon us as engineers and architects that our work will be still in use when we're long gone. And so really we need to be designing these buildings for the conditions perhaps in 30, 40 years' time. So in that regard, we're using global climate models and regional climate models to look at how the climate may be changing in the Gulf, particularly wind speeds. And there you go, that's the end of the postcard from the Gulf. I hope you found it interesting. Thank you.